I've got 10 things that I think you should know about quantum and machine learning. There's a lot of cool stuff in this field. It's a pretty new field. Well, it's not a new field. It's actually quite an old field, but it's new in the sense that we're starting to actually see some real progress and concrete advancements in this area. And so I'm here to sort of break down a lot of this and try to help you understand some of these fundamentals and how you can apply these to your big data and machine learning workloads. And just to manage expectations, we aren't quite there yet. So at the end of this, I've done this talk once before in London, and the term that one of the people used to describe this talk was bonkers. And so that's a British term for crazy, I guess. So there are lots of crazy ideas here, but just bear with me. Let's get through the fundamentals. I'll show you a cool demo as well too at the end, and how to use AWS to actually try out some of these bonkers ideas. And so check out the book too. We actually do have a section in there about quantum. This book was released earlier this year. It's totally up to date, about 500 pages. I think a couple hundred code samples, 250 images. It's insane. It's a bonkers book. So check it out. All right, so the best way to think about quantum and quantum mechanics is that it's nature's operating system, right? So this field is a combination of many, many disciplines. So there's quantum physics, there's electrical engineering, of course, chemical engineering, material science, thermo, photonics, of course, our favorites, linear algebra, and probabilistic methods. And that's just a few of them. Einstein calls quantum mechanics spooky, or called. He is no longer with us. But he, in his own words, said no reasonable definition of reality could be expected to permit quantum mechanics. Still lots of internal debate. In fact, I just got off a call with one of the heads of the Amazon Bracket Quantum Service, and he and I were having internal debates about this. So there's a lot of debate within the actual quantum academic community, as well as the practical and the applied side as well too. Also keep in mind that there are lots of hardware limitations to quantum. And if you think about how the world was with transistors, way long ago, that's really where we're at with quantum. It's trying to trying to capture this power into something that can be manufactured, that can be scaled out, and can ultimately end up in a small little iPhone like we have here. So some of the quantum fundamentals, and you'll see this in the upper right here, which I think might be actually blurred out by something, but I show this in multiple places, so don't worry, you'll see it here in a bit. But the first thing that we have to do is, to start, there's this concept, or this physical construct called a qubit. And so think of it like a bit, right? Like a physical bit, a digital bit that we are familiar with. And this qubit can really be in this linear combination of a 0 or a 1 probability. And so, but when we go to actually measure the qubit, it then collapses into either the 0 or the 1, okay? And so some of you might recall the Schrodinger principle and that kind of thing. And it is certainly related here. I don't bring it up here much because it's just another buzzword that isn't really that important for the way that I present this. So this qubit, and the whole idea of quantum is to put these qubits into what's called superposition. And that's this probabilistic state. And what you're trying to do also with these quantum algorithms is you're nudging those probabilities to get closer to 1 or closer to 0. Okay, and so, but now keep in mind that when you do go to measure, that qubit does collapse into 0 or 1. So it's not actually true. Some of you might have heard that a qubit and superposition is a 0 and a 1 at the same time. And that's not technically correct. And this is one of those internal debates and internal, external, practical, sort of theoretical differences in. So this quantum community, I've come to realize, by the way, is very precise in the way that they describe things. And if you don't describe it in that precise way, you won't really get very far. So I've actually had to, figure out how these things are presented, and hopefully I'm sharing those with you here today. And so there's also this concept of entanglement, and this is really the spooky part Einstein was talking about here, which is two qubits can actually be connected such that when they're measured, they will both go to the same state 100% of the time. Even if they were in different, probabilistic states separately thousands of miles away, they can be entangled such that they both collapse to a 0 or both collapse to the 1. And so I measured that, or yes, I mentioned we are constantly trying to nudge these probabilities and nudge, nature's operating system into something that we can use and train models or solve, large complex linear systems of equations. And the way that we do this is using waves. And so we can use constructive and destructive waves that can help to amplify or de-amplify and nudge these probabilities. And so just like in classic, digital bits, we have circuits, right? And we have like algorithms. And so that's the same with quantum. They're called gates and they're called operators. And these are what we use to do this nudging. And oh yeah, I should also mention that there is this photonics subset of quantum that actually uses photonic pulses to do this nudging. And so when you talk about quantum, I actually have a slide on this later. There are different implementations of quantum. So it would either be superconducting, supercooled, which is classically what we see when we see the Google and like the IBM, those like images of a quantum computer. But there are also photonic based like implementations and hardware that's using light to do this nudging. A couple gates that you should know about. There's one called the Hadamard. And this is what actually puts our that qubit into superposition. Okay, and that's typically H, and that's somebody's name, very famous person's name. And then there's also controlled knot, so C knots. And so just like we have knots and in like classical digital bits, there's something called a controlled knot, a C knot that entangles two qubits. And it's basically like if this first qubit is this value, then that it is now entangled with that second value. Some like algorithms to know about. So these algorithms build upon these gates and these operators. Shor's algorithm, this is what you'll hear and read quite a lot about when you read quantum, where they talk about how to perform prime factorization with at like quantum scale and with quantum hardware. There's also quantum walk, where we're walking a graph, for example, determining the minimum path between two like vertices in our graph. So very common algorithm to implement. Also, Grover's search algorithm. Grover's search algorithm is the basis for quite a lot of other more advanced algorithms, and really for specifically optimization problems, and really builds on amplification, which we discussed with the constructive and the destructive. And so there's examples here. So you see in like the upper right, where that image, that first section I was talking about, where we nudged a little bit and got 51%, 49%. You see on the right the image of, really there are only about 12 operators. 12, is there 12 there? Maybe 10 operators. And with those, you can now construct, many hundreds of circuits and then other algorithms. And then, yes, ultimately bottom right, we see the results of a Grover search algorithm where one of the results is now the most amplified, and that is the answer. So with like 81.6% probability, that's the right answer. And what we've done is through a series of gates and these operators, we have nudged and used quantum to solve our problem. So let's talk about quantum eras and this term quantum supremacy. So we are in the second era, which is called noisy intermediate scale quantum. So NISQ era, that's where we are. If you look at that chart on the right, it's the big black area there. The first era was more where we were simulating. And now we are at the point where we are seeing moderately useful apps and actually have an eye towards this concept of the advantage, where quantum does have the advantage. So these are sort of loose terms. They were coined, I believe, by Google. Quantum supremacy, which we theoretically just crossed over, I believe, in 2019. And that was a pretty easy, simple problem. But we showed that the quantum computer could do more than a classical supercomputer. Okay, it was a very a super simple problem, not very useful to businesses applications, but did show that we reached this state of supremacy. But we really want to be at the advantage, where we see linear speedups and then hopefully exponential speedups over classical computers with these modern machine learning like algorithms. And so keep in mind too that the final era will be this error corrected. So I should mention that noisy means this hardware is still pretty noisy, right? So trying to capture nature's operating system is not an easy task and requires supercooling, requires a lot of special hardware, custom built hardware. And we are not at the point where all of our qubits can be utilized fully. In other words, we need these extra qubits to actually, help fix this error and do the actual error correcting. So very similar to error correcting RAM. And back when we used to pay attention to that, like we don't really pay attention to it today. It still happens. There's plenty of hardware now to help correct those error on these modern RAM chips. And so one thing to note is we are at the stage of about 100 qubits, maybe getting to 1,000 qubits here soon. So below 50, not very useful. Between 50 and 100,000 could be useful. 50, not so much, but. And then of course, greater than 100,000 will, in theory, these numbers are all just sort of, you should think of them more as like orders of magnitude versus specific numbers, right? But just keep in mind that until we can solve the problem of like error correction, we really can't use all of these, these qubits. And now so 0.5 here is quantum data, QRAM, and then, of course, error correction. So classic data has to first be put into this probabilistic superposition before we can operate it inside of this, this quantum computer. And so keep in mind that 30 qubits does require 16 gigabytes of RAM. And we can simulate that because we have modern hardware that one single instance can hold 16 gigs. 16 terabytes, 40 qubits is needed to store 50 qubits of data. Yes, we need 16 petabytes. And now we're starting to exceed what we can simulate, right? So, and I'll talk about simulators here in a bit. And of course, yes, Amazon Bracket does have simulators, but they're more in the 30 to 40 qubit range because of these RAM constraints. And so without QRAM, by the way, and this is really how things are happening today, every time that we execute a circuit, that data has to be converted from disk or from classical bits into superposition, right? It has to go through this Hadamard gate. And if we have to do this every single time, I mean, think about trying to do this with 16 gigabytes, 16 terabytes, 16 petabytes. just to run, a single algorithm or one pass through the algorithm, right? Because keep in mind, we are typically going one pass through and then making a small change, doing another pass, classic sort of like hyperparameter tuning, or just going through the data set multiple times to do multiple iterations. And so this is a huge barrier to trying to achieve these linear and exponential speedups over classical supercomputers. And also keep in mind that classic sort of redundant error correction is difficult because there's this fundamental concept of quantum mechanics called no cloning. You can't actually clone matter. But if you could, we would be living in a very different world. There's a lot of crazy things you can think of there if we were able to actually clone. And so with quantum mechanics, just know that there is a no cloning principle. There are tricks to do error correction, and there's a lot of research in this area. Because really, without QRAM, we would have to do this conversion every time, and it's infeasible to do anything useful when we have to continually go from digital to superposition. That's where all of the time will take place, because once you actually get it into superposition, then those operations happen pretty quickly. So let's talk about hardware differences. So I mentioned earlier, there's superconducting, there's something called trapped ion, and then photonics. These are really sort of the high level differences, and a lot of companies in this area now. Of course, AWS, being AWS, they like to give options to their customers, and so they support superconducting and trapped ion. There's 3 companies right now that we work with, and hopefully more coming. And there's different methods. So there's like the like gate based is the version that we've been talking about up till now, where I showed you gates being chained together into circuits. There's also annealing, which is D-Wave actually does quite a bit of, that's their whole method, and they claim to be superior in terms of like optimization problems with the annealing method. We will talk about gate-based. It's really the one that is closest right now to the integration with these machine learning libraries. So yeah, Amazon Bracket supports these. So here's one image here. So there's D-Wave, we have IonQ, that's the trapped ion, and then superconducting by Rigetti. Also, it is public knowledge now that as Amazon is working on their own quantum computer, and I believe it'll be superconducting based. And if you go through the Amazon job postings, you could pretty much figure that out yourself as well too, based on the types of people that they're trying to hire. All right, let's go to quantum programming SDKs and simulators. So here's where the rubber meets the road, if you will, as the saying goes. So this is where us as developers, we want to know, how do we get access to and start to build these quantum algorithms, or even just simple circuits. And so there's something called Open Chasm with a Q. Yes, everything, of course, in quantum starts with a Q, or has a Q somewhere. And this is really the assembly language, if you will. And this was pioneered by IBM and now is now open. It's not very readable, just like any assembly language. It's just kind of cryptic. You can kind of make it out if you're, willing to spend the time doing that mental mapping. Or you could use something called Qiskit. And Q, so that's Qiskit. This is also by IBM. It's a layer on top of Open Chasm. And I believe it's public now, but yeah, Amazon is supporting Open Chasm. And so we are working on the Amazon Bracket APIs that actually sit on top of Open Chasm. And so similar to how IBM Qiskit sits on top of Open Chasm. And very, very well documented, by the way. Qiskit is super well documented, lots of examples. Yeah, IBM even has this summer school, quantum school. I highly recommend that you check out. You have to basically be there the day that the link goes live, otherwise you won't get in. I don't have a link offhand, but if you Google IBM Quantum Summer School, you'll be able to find it. And so, Google being Google has created their own SDKs and, specific for their Google hardware, for their Google quantum hardware. I haven't heard much about them supporting OpenChasm. I don't even think that they're involved much. I could be wrong, but I should double check that before saying, but they do have their own APIs. The cool thing about Google's APIs is they are actually now part of TensorFlow. And so TensorFlow now has this library, TensorFlow Quantum, that has these optimized hybrid algorithms that can do, sort of classical machine learning and only use the quantum computer to do quantum optimized operations. And so, of course, you still have to get the data in and out of superposition, but in certain cases, it's worth it. And so definitely check out TensorFlow Quantum. There's also, of course, the Amazon Braket SDK that I mentioned. The benefit of the Amazon Braket SDK, if you are already using AWS, with just a single line of code, you can change the hardware, like I showed earlier. With a few lines of code, you can integrate with Amazon S3 to get your data from S3 into superposition. You can, so Braket natively integrates, of course, with like IAM security and, of course, CloudWatch for the logging. And so you have all of the fundamentals. You have data security, you have different hardware, and you have logging all built in just by using that SDK. And of course, Braket SDK does support OpenChasm. Now, Penny Lane, this is by a third-party company, but it is open source. A company called Xanadu with an X. They're out of Canada. This is also open source quantum machine learning. They support TensorFlow, PyTorch. They have plugins for Amazon Braket, for all the hardware supported by Amazon Braket, for the Google Circ hardware also. So check out Penny Lane, a lot of really cool examples. That company, Xanadu, by the way, is one of the companies pioneering the photonics version of quantum. So check that out if you're interested. And then also simulators. So all of these APIs have some sort of simulator that you can run, and basically simulating on classical computers. Some use GPUs, some don't really need the GPUs, but they support these 6 or 5 APIs, 6 APIs, and can actually run your circuits, your like quantum circuits. They are limited, though, of course, to 30 qubits, maybe 40 qubits. The other cool thing is that they can simulate noise. There's literally a flag that says noise equal true, or noise percentage equals 10, something like that, that can simulate the randomness and the noise. Sorry, not randomness, but the noise that is coming into the quantum computer, which is very sensitive to the outside environment. These are the simulators that are currently available. So we see 34 qubits, 50 qubits, and then 17. So maybe check out some of those. And let's talk about quantum machine learning algorithms. And I've got about 6 minutes left, so I'll probably have to share the link to the GitHub if I don't have time for the demo, but I'll at least show it to you. So yeah, quantum machine learning. The cool thing here is with these hybrid algorithms, we can do things in the near term and just do short bursts of QPU computation. So similar to how we would do like GPU computation using the NVIDIA GPU for certain things, but still be coordinated by the CPU. So for example, all the if statements, if something, then this, that's all on the CPU. But then we would then dish it off to the GPU to just do massive parallelism. And so a similar kind of thing where we would have QPU that we pull in. Quantum machine learning research has actually inspired improvements to classical algorithms. And so there's this really cool archive paper here, Quantum Inspired Classical Algorithm for Recommendation Systems. There's also a variant of gradient descent called quantum natural gradient. And so by studying these things in this newer quantum world, and we can actually make changes and improve classical algorithms. And so we'll see there's quantum variational algorithms that train circuits like neural nets. So we can actually do similar to neural networks. Principal component analysis, support vector machines, clustering, linear regression, binary classification, quantum neural networks. Now, just to be completely upfront, these are very slow. these are not going to beat your classical right, like versions of these algorithms. And so, while it's fun to get binary classification going, which is what my demo does with quantum, also keep in mind that it is slow and it's a little bit right now expensive because of the cost of the hardware. So, definitely stick to the simulators. Those are cheap. Those are, relatively free, basically. You can just do it on your own laptop. Like you can actually run one of these simulators on your laptop as well. All right, so here's the binary classification. So, from a Jupyter notebook, this is the demo. Actually, let me get to the rest of the slides here. Just do 9 because this is pretty important at 3 minutes. Quantum use cases. So these are theoretical use cases. Cryptography and factorization. So not to scare you all, but I'm going to scare you. It is theoretically possible to break the 2048-bit RSA encryption in approximately 3 minutes with quantum. Now, there's a lot of asterisks here, and this has been revised over the last couple times I've done this talk, but we would need 6,000 clean qubits, and clean qubit is error-free, noise-free. That translates to about 1 million noisy qubits, and we are nowhere near that. And also, so chemistry, material science, right? So doing simulations, doing protein folding, these are very, very high dimensional complex problems to solve. We can do them like relatively quickly with quantum. Quantum has the ability to massively scale and perform many, many optimizations and can do protein folding very, very quickly. And let's see, optimization problems, search and rank. And so, 200 clean qubits for simulation, maybe 100 for optimization problems using Grover's algorithm. But just know that we're still pretty far away. So the highlights for quantum: potential for massive parallelism beyond, right, like anything that we've ever seen today with classical computers. Can operate on many qubits at once while in superposition. Yes, I mentioned that there are theoretical speedups for certain classes of algorithms. So, back to the big O notation, ON goes to O log N, for example, which is a huge performance savings. Now, lowlights: current qubits do not hold state very long. So up till now, we've been talking about mostly the number of qubits. We've talked about the error in the qubits. Just know that these qubits cannot hold that state for more than maybe just a few nanoseconds or a few milliseconds. Current circuits, therefore, cannot be very deep. Right now, maybe 100 to 200 gates at the time of this talk. Current hardware is still very noisy, very sensitive to the physical environment, which is why these things need to be super cooled. Okay, so. And I guess I'll just post the link here in the chat. Thank you so much. There is long-term potential here, just huge long-term potential. Currently not a lot of real-world apps, but you want to be part of this quantum flywheel, and you should start to learn this stuff now. Yeah, check out Qiskit, check out Amazon Bracket. And as more people come online to this quantum world, we start getting better hardware, we start getting better algorithms, and things get cheaper and the flywheel spins. So thank you much.